Graduated in instrumentation technology at MIT Madras during 1961 to 64. Now, BTech and part of Anna University, Chennai. His association with MI India is a senior life member of ISA. According to the professional domain, the process instrumentation and control design, construction, commissioning, maintenance, project management training, all those things is handling. Organization which he has worked in, I think throughout the world he has worked Indian wing of UK multinational Imperial Chemical Industries, UK, Reliance Industries, and ICI India, Rubber Chemicals Explosives, Reliance Industries, and the overseas assignments. Since from 1975, he is taking the overseas assignment, and training impacted many trainings he has impacted. And I welcome today's resource person with an honor on behalf of Electrical Engineering Department. I welcome you, sir.
Thank you. You can tell me when I can speak. I can speak now.
Yes, sir. You can. Yes, sir. You can go ahead.
Yeah, I'm addressing all the participants and seniors. Good morning, everyone. I am absolutely privileged to be, talking to you people who are in the academic and reached great heights. And it is my privilege to share the knowledge which I have acquired, so that you compare your academic knowledge on this subject with respect to what we are going to share today, and maybe you would come out with a lot of ideas for your own internal academic project work, innovative work, etc. Because in academics, you can go only up to a certain point because you don't see the physical working or the environment of the concerned equipment. So this is my opportunity, and I must thank all the organizers to give a practicing engineer like me a platform to share all these details with respect to control valve. So I begin by saying that the control valve is being taught along with the control systems. But, I have always found that the coverage of the control valve in academics cannot be very elaborate.
Sir, Krishna, sir, unmute yourself, sir. Hello. Sir, unmute yourself. Sir, unmute yourself.
Hello, sir. Can you hear me? Sir? Krishna, sir? Okay. You can unmute him, no?
ಇಲ್ಲ ಅದು ಅಟೆಂಡೆನ್ಸ್ ಮಾತ್ರ ಅನ್ಮ್ಯೂಟ್ ಮಾಡ್ಕೊಳ್ಳೋಕೆ ಕೊಟ್ಟಿದೆ ಅವಕಾಶ.
ಓಕೆ.
Co-host ಅಲ್ಲ?
Host. Sir?
One second, ಕಾಲ್ ಮಾಡ್ತೀನಿ. Hello. Sir.
At the bottom of the screen, you'll find unmute.
Unmute me, I pressed. Okay, is it okay? So I'll continue with the...
now is okay, sir. Now is okay, sir.
Yeah. Sorry for the hiccup, because I'm quite new to this. Right. Is my voice clear, sir?
Clear.
Yes, sir. Your voice is clear, sir.
Clear. Clear.
Yeah, please tell me or call me if there's any problem. Sorry, I'm not able to settle down.
It's okay, sir.
Control valves are the population of control valves is very much in the petroleum refinery, heavy chemicals, power plants, steel plants, and every other device would be a control valve. So I thought it is fit to teach the academicians, not teach, sorry, share the knowledge with academicians so that they get their own industrial picture and you all know what to do with this kind of knowledge that is being discussed today. So we start with the first slide. The first slide is giving you the ambience or the environment of a typical section of a petroleum refinery. You don't see a control valve here because it is probably hundreds are there, but you cannot see it. But this is the general working environment of the oil refinery. Now, next we come to see what we are going to discuss for 90 minutes today. This is a typical control valve which is installed in a refinery, and I will discuss every part of it so that
Sir?
at the end, yeah, tell me.
To disturb you, sir.
Yeah.
Can you please share your slides, sir?
Yeah, I am already doing that. For that, have I pressed anything which is I should press it?
Slides are not seen, sir.
Okay, no, how do I just go out
Sir,
of this?
actually, you are not. 1 minute, sir.
Yeah.
Sir, HPK, sir. You are the presenter. Hello?
Yeah, hello. Can you make me the presenter?
You are the presenter now, sir.
But the slide, why it's not coming? I wanted to know that.
Try again, sir.
No, I am minimizing.
You have to share the screen, sir.
Yeah, where is that control?
At the bottom of the screen, there is a share is there now, sir.
Yeah. 1 second. I'm not able to get that. That's the problem.
Sir, are you in the full screen mode?
Full screen mode. 1 second. See, only mine is coming.
Just escape.
My screen is coming prominently. I'm not able to see what you are giving me. That's the problem.
So once you press escape key, sir.
Okay, I'll do that. Done.
Now it is done, sir.
It's done, is it?
Sir, again, HPK, sir, you have taken the presenter. You are the presenter. Please change that. Sir. Sir, now you are the presenter.
Okay, I can you see
Share
it now?
screen. No, sir. We can't see it. Screen is not seen, sir. Try again.
What do I do now?
Share screen button. Can you see on the screen, sir?
No, I'm not able to see that. That is my problem. Otherwise, I'll press that on now.
Press escape key once, sir.
Yeah,
once or twice.
Yeah. I've done that. Can I minimize this first?
Yes, sir, you can do that. Yeah.
But shall I start from beginning again then? Otherwise.
Yes, sir. I will do one thing, sir. Rejoin that one, sir. I think that is better.
What I'll do is I'm not able to get that normal buttons you have, leave the meeting, that all that is totally, I've just go out of the meeting by.
Yes, sir.
And join again, sir.
Rejoin.
Sir, can you see drop menu, sir?
Join meeting.
Yeah.
But now I press share here. Okay. And it's
Hello. Sorry, so,
Sir,
hello.
sir, you cannot log in from 2 devices, sir.
okay. No, I don't have any other device.
Phone. So you're muted.
Sir, switch off, login once again. Switch off and login.
Professor Prasanna Kumar. Prasanna Kumar. Prasanna Kumar.
Sir. I'm cutting that one, sir. Wait, sir. Wait.
Maybe you can share the screen.
Sir, that's what I'm going to do now.
Okay.
He has to unmute himself. Mr. Sir.
One second. Yeah, screen is. Yes. Maheshan?
Yes, it is visible. Visible.
But sir is in mute. Sir has muted himself.
Okay, no problem. Unmute one, please, sir. No. Not unmute. Unmute yourself, sir.
I'll send the request. You can click on that. I have sent the request. Sir can say okay.
So I'll wait a second. I'll come out from the slide share. Sorry, you'll correct that one. Sorry for this one. Okay.
Hello? Hello? Can you hear me now?
Yes,
Yeah,
sir.
sir. Now you can hear.
Now can I press share the screen? I can press now?
Yeah, you can do now, sir.
Okay, I'm now doing. I press the screen, share screen. But, and then can I share the screen also?
Yeah, sir. You can share now.
Now it's coming?
Coming now.
Yeah, I press the share the screen. Again, I press. Screen.
Not coming, sir.
Not
Sir,
coming.
did you
No.
now it's
Coming,
there.
sir. Not coming.
Is it coming or not coming?
Coming, sir. Coming. You can continue.
Okay, sorry, my apologies for all this disturbance, you know.
No
Can
problem,
I-
sir. No problem.
Can I continue now at last?
Yeah,
Yes,
sir.
sir.
Okay. This picture of control wall is clear to you there in the screen that
Yes,
side?
sir.
Okay,
Yes,
I'll
sir.
start talking. So
Please
this
be in the presentation mode, sir.
Maheshan, okay, that's come.
इधर महेश इधर आओ
yeah, you
sir
want
is there in
me
the present.
to put it in the slide board?
No, sir. No, sir. You can continue, sir.
Yeah,
No,
I
sir.
better leave it like that because it will further delay everything.
Okay, sir. You can continue.
Yeah. So this valve is a typical control valve which is on a pipeline in a refinery. And I'm going to talk every aspect of it. And the entire presentation has got 3 parts, which I'll be explaining when I go to the other slides. Did you see the next slide, which is called valve? Is the next slide clear to you? Hello?
Sir, yes, sir. Clear. You can go ahead.
Okay. Yeah, I'll come back to this slide. Now I start a presentation. The objective of presentation is to present control valve of the industrial environment so that teaching facility can appreciate application issues and demands of the process. That is, your academics already are teaching control valves in some form or the other. And this discussion would help to further enhance their knowledge. The teaching faculty may like to introduce excerpts from this knowledge sharing exercise while they're covering control valve as a final control element. Okay. The 3 parts of this presentation is first part, which you are going to see now. I find some echo coming. Is it because of me or is it because of something that side? Hello? Am I audible?
Yes, sir. Audible. You can continue, sir. Audible.
Yeah, some echo is coming. I don't know from where, but I'll continue.
Okay, sir.
The first part is principle of control valve, operation and types of control valves with their special features. Part 2 is the control valves in the process control loop, basic formula, valve characteristic and aspects of sizing. And part number 3 is control valves on difficult process application. Now, when you share all this, the teacher or the professors or who are teaching all these control valves would be able to, against the backdrop of their own knowledge, view this and further get more ideas. That is the object. Now, first thing is, what I would like to emphasize is all these days, in so many sessions, you would find that we are on a micro kind of a level with intense discussions on nanotechnology and various other systems which are more on the micro level if you look at it. And the discussions were fantastic. Now I'm taking you into another journey and start with a macro level, because why am I talking to you about control valves is it is part and parcel of a heavy chemical industry, including refineries and other petrochemical units. And the people who graduate from any discipline, if they find a assignment there or in the consultancy like Tata Consultancy or Engineers India, you would find that this topic is a very, very hot topic and is required by any engineer. It may not be emphasized much during the academics in any part of the country, but this is a unique item. And if you could acquire some knowledge on this, it will be very, very helpful. As I said before, the control valve population is prominent in process industries. And then the other one is, what is the role of a control valve in a control loop? Next point is control valve function, types, and special features. This is what is covered in part number 1, which I'm just starting. Right. And now I will take you back to that slide for a minute, which is going to be the governing slide. You may be surprised. This is a simple valve with which all of us are familiar with. And this valve basically has got utility in our day-to-day life. For example, even in our wash basins or a kitchen. And what it has got mainly a handle and a kind of a screw, and then you got the a disc or whatever you call it, and by moving it up and down, you're able to regulate the flow of water. This is the simplest form of a valve, and if you work on it more and more, you will start understanding the control valve and what it has. So this is the basic one. Obviously, it's got a handle, which I will call it as an actuator. Then it's got a body, and then the handle carries a spindle, and the spindle has got some kind of a disc, and this disc is going to rest, stop the water, or gradually move so that you can get varying flows of water. That is the way this valve is designed as a simple valve. This multiplied by n times becomes your control valve. So we are going to talk about that. And before we talk about that, we are going to say now the control valve in the laboratory is what everyone has seen in the case of academics. And they themselves, all of you are familiar with control valves because you do number of experiments. I've seen it in 1 or 2, 3 colleges in Bangalore that they have a very good lab with the control valve. It's not that you people are not familiar, but it is very important to know how does it really function and what are the problems when we go out of this lab or the academic environment. Now, it's like learning driving, and in the initial days, you are only practicing in a quiet road. And this quiet road, you master the vehicle driving. And later on, when you go to a busy road, like those who are in Bangalore would know the traffic pattern in Hebbal side, flyover. And you would know the kind of maneuvering you have to do and the kind of distractions and all the kinds of attacks on the car in terms of speed, closeness, etc., etc. Now, this scenario is similar to what a control valve actually sees when you go to an industrial mode. So repeating, the control valve in the lab mode, it works and everyone understands its function. There is no amount of disturbance there. Everyone works on it and understands it. But that is not the aspect we are going to talk about now. So what we say is a control valve can be defined. Now, since you've seen that small valve, and now if you put your mind onto it, you'll say control valve has been defined as a mechanical device that fits in a pipeline, creating an externally adjustable variable restriction. So what you do is, forget the laboratory, and you take this control valve device and you put it in an industrial complex where it is actually installed in a pipeline and it is functioning exactly like a variable resistance. Now, in the variable resistance, what you do is you operate that knob and move the resistance so that the current changes. In your other small tap that you saw, what you do is you're moving the small handle and adjusting the amount of water that has to go to the sink. Now, the same thing in a larger scale is what a valve does in industry. Now, if you do look at the small valve that I showed you, that is a mechanical valve. So you have similar valves in an industry which can go up to very large sizes. For example, globe valve sizes can be, for example, control valve, globe valve, which you're going to see, I have seen sizes up to 14-inch pipeline. Okay, and then on other valves, you can get higher and higher diameters. So ultimately, it's doing the job of being a variable resistance in a circuit That is what circuit? It is a circuit which is powered by not your current, but flowing liquids, flowing gas, flowing steam, two-phase liquid, etc., etc. So that is what it's doing. So it's basically a variable resistance, but it's of a mechanical structure. Now, I again take you back to the refinery, petroleum refinery, which I happened to work for a long time, and I worked in a very, very large refinery, which is belongs to Reliance in the Jamnagar factory. Now, there, that is a very large one, but if you take a medium-sized refinery, petroleum refinery, you could get approximately 2,000 closed control loops. Now, this 2,000 closed control loop could mean, and probably will mean, 2,000 control valves. So you could imagine the population of control valves in a refinery or a petrochemicals. Now, typically, a very large petroleum refinery with number of sections could have 1 lakh input outputs, which I have seen myself. So I can be confident of this figure. So what does this slide tell you? The slide tells you the following as students and also the esteemed teachers, that this control valve, any amount of instruction that is given on a control valve in the academic curriculum is going to help the student when he goes for a job outside, he would definitely be appreciated for his knowledge of control valve, even when he left the academic environment. B, if he wants to go for higher and higher studies like MS and PhD, you got abundant scope in the very nature of control valve operation with respect to the industrial atmosphere, which I'm going to tell you, to do his job in MS projects, and even there are topics which can be generated for PhDs, which I'm going to slowly tell you at the end of this session. Now, this tells you, this slide basically is to prompt you and tell you that, yes, this control valve needs a very special status in teaching and also practice because of its importance in the process industries. I am biased with process industry because all my life, in fact, I started working in the year 1965, and then I actually retired by about 2009. I did multiple times. I was called back, but and even today, I'm fond of my line, which is process automation. So I've been very closely associated. Naturally, my thoughts will go only to the process industries, where let me tell you that there is immense scope for the control and instrument engineer to grow. And not only hierarchically, but in knowledge. Because some of my juniors, if I can slightly digress, have left, they were working for Reliance, they left after the experience, and then they have joined the Gulf, and they are gone into a fantastic heights in technology and also in status and hierarchy. So that is the kind of scope that the process automation offers. So I would like to again emphasize this point. Now, this is something which is very familiar, which all of you know, and I don't have to do any talking because I'm only taking a small portion of this. First, I would like to acknowledge through this forum and this presentation, the lecture that was given by Dr. Prakash on the controller, PID controller, is the background to, and he did a fantastic job, and followed by Dr. Anuj Abraham yesterday, who again dwelt on the various types of PID controls that are available. They both explained beautifully. I would like to acknowledge and thank them, because today I will not touch on that subject because I don't think I can add any value, and it's not necessary also. So I'm now going into this final control element bit that is called a control. The control valve is called the final control element. Now, and to be very frank with you, during control theories, this valve is not given the importance that it should get, because it is not relevant while you're talking about Nyquist criterion, stability, body plot, and etc. All your Laplace transform and the mathematics associated with it, because it's not relevant. But you will tell me at the end of the discussion that you can get into modeling with, and I can suggest a few topics for which you can build models for the same control associated problems. Now, this is a very simple slide to tell you, just a kind of refresher, to tell you this is the place of the control. Everyone knows what a control loop does. I don't want to add any more knowledge on that because it will become totally redundant. So this is where we come from. I start from here. The controller gives the output, and this FY and the other accessories on which I'm going to talk about are all, and this val is what we are going to talk about. Now, if you see that very small example of that val which I showed you, now we are slowly developing that val to look like a control valve. And how we are developing, you're going to see in the slides that come. This is nothing new, and I may even skip this slide because basically it's telling you the control valve receives the inputs from the controller, and I'll start from there if you don't mind. But anyway, I'll go through it, doesn't got time. Process plants consist of hundreds or even thousands of control loops, all networked together to produce end products. This screen has got hidden. I think slightly I must move that. Each of these control loops is designed to keep some important process variables such as pressure, flow, temperature, etc. within the required operating range to ensure the quality of the end of the product. Now, the next thing is important. Now, all this is known in the laboratory level. Now I'm going to lead you, slowly take you out of your laboratory and take you to the industrial arena. Now it says each of these loops receive and internally create disturbances that are detrimentally affect the process variable. Other loops can influence each other. Why I'm talking about it is, you got a net in the lab, you got one pipeline, one process, and you got some storage tank of water or whatever, and then you are doing the simulation or you're doing control. But if you look at a refinery or any other chemical plant, you'll find the valves are scattered and each valve has got its own loop. They're clashing. The operation of one valve disturbs the other one unless you do some modification in the PID algorithm, etc. I don't want to talk about all that. Basically, I'm telling you that a control valve in the arena, the industrial arena, is a different ball game, and that's what I am going to talk today. At every stage, I'm going to tell you the difference. This is the problem, etc., etc. Now we go on to this simple ones. Once measurement, comparison, and computation are completed, then some type of final control element must implement the strategies selected by the controller. Control valve is a common final control element in process industries. Gentlemen, can I tell you, ladies and gentlemen, can I tell you one thing? If I come and tell you that the control valve is only the final control element, I'm saying something which is wrong. It's not true. A final control element, you people know all these things, that is, the output can go to a variable frequency drive also. Nowadays, what they do is they alter the speed of a pump or a fan and do much more energy saving than putting a control valve and operating a damper. So I am to some extent biased, and I'm only leading you to control valve because that's the topic of today's discussion. So please remember, if I say the final control element is only the control valve, it is totally wrong. Like Dr. Anuj Abraham was showing such interesting things, which are all receiving PID outputs. And none of them, we even find a single valve. There are other devices which are acting as final control element. And in the complex thing, he explained it so well. Control valve manipulates a flowing fluid. When you say fluid, many people think it's only liquid. No. Fluid is gas, steam, water, or chemical compounds to compensate for the load disturbance and keep the regulated process variable as close as possible. Now, there comes the oversimplification. So it's not as peaceful as we can think because of one reason. I think I'll cover it right now. Yeah. See, what did we say about, please bear this in mind. What I'm telling you, it's very, very important to understand. Don't take the control valve for granted, because you think that the moment the message or the instruction comes, the control valve operates and it is everyone is happy. No, because there is tremendous bombarding by the process media. Because just above I read that it contains gases flow, liquid flow, steam flow, turbulence, all kinds of things are happening. And the valve is installed there, but it's receiving very quietly the controller output. But what it has to manage is the process media. When I say manage, you have to manage so many things. If you talk about a liquid, because it's very easy and convenient to talk about a liquid, the hydrodynamics of the liquid. That is, you have liquid gushing in, sometimes coming as two-phase flow, that is gas and liquid, and the pressures that we talk about. Gentlemen, one more thing I'll tell you. Let me give you the feel of pressure. All of us, I think without exception, knows been to the kitchen sometime, either working or observing. Now, a pressure cooker has got, when you hear those sounds of release of steam, it is approximately 10 pounds per square inch. Okay, gauge. Approximately. I may be wrong, some may be more, some may be less. So that order of pressure itself, you cannot lift a handle, lift the lid, because it's impossible to lift. That's the pressure. Now, I'm taking you to another place where I have worked also, and to give you an idea of pressure that the valve has to manage. Why I'm talking about this? I'm talking about how the valve has to manage the hydrodynamics. And the hydrodynamics in this case, I'm giving one example, is before the valve, pressure is 3,000 pounds per square inch. Before the valve. And after the valve, that is the outlet of the valve, it becomes 300 pounds per square inch. Now, what is the difference between P1 and P2? So that energy has been, the potential energy at that point of time pressure has been converted to kinetic energy. And you can imagine the flow rate inside imagine the whole valve is made out of glass, the flow rate and inside and the turbulence. That doesn't happen in the lab, because the lab, you've all got comfort pressures and you don't see all this. So the controller has to receive the instruction from the controller. Number two, manage the disastrous hydrodynamic and aerodynamic. We talked about gases. So the valve has to, when you say manage, what do you mean? It has to make sure that the valve integrity doesn't allow leaks. It also has to make sure that the valve movement is not hampered by the hydrodynamics. And also it should not leak to the atmosphere. See, a pipe, small valve which I showed you again, going back to it, is if the leak takes place, it's only going to be water spraying in wherever the valve is, whether it's the kitchen or in the bathroom sink, wherever. So that nothing happens. But in this case, you can imagine the kind of liquids that are being carried. Sulfuric acid, nitric acid, naphtha, LPG, liquefied petroleum gas, you name it, everything. And if they leak, you can get into a different one, which I'll explain tomorrow when I do safety instrumentation. Right. Now, I talked to you about the agony of the control valve. We'll go to the next slide and get a little more organized. So I told you that the media is not that straightforward. I will explain to you only the hydrodynamics. What about the temperature? What about the pressure? What about the corrosion activity? All these questions you are asking, I'm not answering, because I'm going to answer it at the third slide. When I go to part number 3, I'm going to answer. So that means the process media is not straightforward. So the controller has to work with all the constraints and produce the results, which means where are the results? It's in the control room. When you go to the screen and you see the control beautifully working, which Dr. Prakash was saying that how the algorithms make sure the set point as well as the measurement point both coincide. So it's easily said what agonies go through in the industrial atmosphere is what I'm emphasizing. Now let's come to a control valve and take a picture. Now I'm graduating from that simple valve which you saw with a small handle, and then I was very happy describing that. Now we go on to the real valve. This is how a control valve actually looks. What you saw, the green valve was not very clear. It gave you the idea of what kind of a animal it is. That's all. Now we are going a little bit more. Then I say any valve, control valve, has got three elements, three assemblies. Sorry, one is called the actuator. The other one is called a positioner, and the other one is the valve body. You saw in that slide, I don't think I have to take it. There was a stem which was moving down because you were turning the handle, and that was having a screw. So that was here. The same spindle is going to move up and down. So it's called a sliding valve. And the sliding valve moves up and down from, how does it move up and down? The 4 to 20 milliamps from the control room is coming into this black box, which is called as positioner. It does some very clever things. It takes that 4 to milliamps and internally gives output and finally converts that output by the black box inside to an equivalent pneumatic pressure. Why pneumatic? Because this actuator works on air, and this is the first stage of an actuator, a pneumatic actuator, which is very, very complex. If I start describing that, I can describe it for 2 hours, but that is not relevant and it's not necessary also. So this pneumatic actuator, you will see a better picture of this because I'm going to explain that also. Because this whole part one is only meant for you to get into the control valve and understand the inner parts. So you got basically the positioner, which I was explaining, receives 4 to 20, and in this black box, it converts English into French. Let us say French is air. So the English to French translation is done in this. And what is that? 4 to 20 milliamps is equal to 0.2 to 1 kg per centimeter squared in air language. The current language is converted to the air language. So because why? This one operates only on air. Then this stem, which you saw in that small slide, is connected to this valve. Both of them meet and they are connected mechanically. So when the air pressure pressing the top, this will press the bottom, press and then this valve will go up and down. Now you'll see that very shortly. Now this one is a positioner, but it is a positioner is very simple to talk about. Okay, the black box, I call it positioner. It is very, gentlemen, very important. Please remember that this positioner is a position controller because it receives the 4 to 20 milliamps and the output is decided by the position. Now, what is the in any controller? You need a measurement. Where's the measurement? This one. The position is mechanically picked up, and some cases electronically also picked up. And what is a set point? Set point is your controller output. So then it gives its own output, and it moves. What is the job? It says, because the control room says, please put the valve on 50%. So set point is 50% at this instant of time t. So it moves it so that it will be at 50% opening. And this is the valve body. Professor Prasanna, is my audible? Is it audible and clear?
Yeah, audible. It's audible and
Clear? No sound.
Yeah.
Right.
Yeah.
I'm going a little speed. I think I'm losing time, but I'll try to speed up because already I have not finished the first slide itself. So I'll do a little fast. This I'll go quickly because we don't have much time. types of valves. This is the organization chart for a valve. The valve is the grandfather, and it's got number of sons and grandsons, etc. So the point is, here you got basically two types of valves. One is your valve, which is sliding stem up and down, and the others are this rotary type of valve. This is rotary type. This is a different type of valve which you're going to see. And then you got other elements which are coordinate to it, which you're going to see also. You have single-seated, double-seated, etc., etc. Now, this is to explain to you control valve so that you understand better, because that actuator, now the actuator has got a spring here. You give air pressure, the spring is opposing so that you get a up and down movement, and this movement, valve stem position, is picked up by your valve position controller, and the liquid goes inside, goes out, goes like this. What is the triangle for? Triangle is the shaped port, shaped plug. The plug is shaped in very many ways to give a certain characteristic which you are going to see as we go on. So this is the basic picture of how a control valve looks. Now here it's a better picture to show you that the blue lines are the liquid, let us say liquid. It goes into this gap between this provide plug and then the other portion which is called the seat. This is the plug, this is the seat. This plug is connected to the stem is connected to the actuator. Now what the liquid goes. Suppose you change the position, then more amount of liquid will go, more opening, etc., etc. So in this case, if you ask me what is the item which I want to emphasize on, I would straightaway say the much neglected item is this brown and this magenta colored thing. This is the gland packing. Now, what is this gland packing is? The liquid here, if this was not there, it will get out in the atmosphere. So there is a packing called gland packing, which varies from the material of the process media, and this goes up and down. It is not only to see, it is also to lubricate quietly. So this is a very important point called the gland of a valve. Now I'm not going to spend much time. This is your body and this is your actuator. Both of them have to be connected. Professor, all these people will get the slides, no, for their as copies?
Yes, sir. Yes, sir.
Okay, fine. They'll have a lot of reading has to be done because I won't be able to go and explain everything. Now, this is how a single-seated valve looks. I can see the spring also. Now, this is a complete valve showing you the positioner and this particular positioner, diaphragm, etc. Nothing very different from what I talked about. Now, the question comes, why I'm projecting this is, this valve looks a little different for you. Globe type, and this globe type valve, there are basically three types of valves. Globe, rotary, and then the diaphragm type. The diaphragm type, let us not worry about. So you basically got globe type, and then they call the sliding stem going up and down, and then the other one is a rotary. So this has got a double seat. Now, the very important point I want to emphasize here is why a double seat? A double seat ensures two things. It allows little more flow because the flowing port becomes two, one side and the other side. But then you are going to ask me, you said there is an advantage. What is the advantage? For the same size, you have this actuator, which is there, is of a smaller size. Then you will ask me, so what if the actuator is small? Because you save money. But then everything is not all that clear. By introducing a double-seated valve and a smaller actuator, the job is done. But it will be leaking in the shut position. And that leak you don't mind. When you say shut, some amount of liquid will go, so that doesn't bother you. And the process engineers also agree. So that is a disadvantage, but the advantage is the actuator size becomes small. This is another type of valve. It is called an angle valve. Liquid in, liquid out, and is used for liquids with solid particles. This is a three-way valve. It is used for mixing A and B becomes product C. It's called a mixing valve. This is a butterfly valve. This disc rotates about this axis. Now, why a butterfly valve? Right. Globe valve, which you saw now, can go up to about 14 inches. With my experience, I've seen 14 itself, it becomes huge. You know, a 14-inch valve will stand at least 8 feet in height. Everything put together, it comes to 7, 8 feet. It will become huge. So what happens is after sometimes the designer makes sure that he is able to manage the economics and also the duty. They go for butterfly valves, butterfly valves can go to very, very, what do you call that, diameters. I have seen 7,000 millimeters, that's nearly 1 meter. And in the in the refining section, the largest I've seen is 9 feet. 9 feet piping with a control valve, butterfly valve. Now, immediately you're going to, I'm going on to a very relevant subject. The moment you say that 9 feet and there's a huge valve, what kind of actuator? I've been only talking to you about pneumatic actuators. Someone is asking me, is there any other actuator? Yes, there are electrical actuators. What happens if the pressure becomes huge or the size becomes huge? It is unmanageable. Can you manage it electrical actuator, rotary actuator, and this pneumatic? The answer is no. Then you graduate to what is known as a hydraulic actuator, which I am not covering. You must know there are 3 types of actuators: pneumatic, electric, and hydraulic. For example, that 9 feet diameter valve, which I have been associated with in the project, it has been there. The actuator is hydraulic, and you know the flow rate of that catalyst dust which goes through that. If I tell you, you will be surprised. It's hot, about 600 degrees centigrade dust and particles which circulates at 1 meter per second velocity through that valve. 1 meter per second velocity, tremendous velocity, because 9 feet, you can imagine the amount of flow that takes place. This is a valve which belongs to the rotary actuators, and you can see this hole will become turned the other way, it will become shut. This is how a ball valve actually looks. You know about the actuator, positioner, etc. Okay. This diaphragm valve is used more in the water treatment plant, where the diaphragm itself gets pressed. You see this blue portion in the, this is shut, open, and then they press it down and shut it. That's the diaphragm valve. We used in pharmaceuticals also. This is another rotary valve, going like this. Another variation. This is also rotary valve. And all of them have advantages which are spelled out in this literature. Please go through it, but I don't want to read it. When you use it, why you use it is all written in that. This is the last, I think one more slide I got, one more point. Yeah, this is your leakage table. You can have a look at it. You see, when I was working, the normal discussion and fights take place because the valve is leaking in the shut position. So in this case, this is in the international standard table, which tells you for what is the leak rate that is permitted for each type of class of leakage. So this is a very interesting table. So a valve will leak, but if it has to be tight shut off, then the manufacturing inputs are to be totally different. Now this is your latest valve position controller. It's a digital valve controller. Now, what is the difference between that and what you saw there in that blue valve? Nothing much, except it's completely electronic, and it is intelligent also. It's able to give you diagnostics which go to the central receiving your PC or to some other device, HMI, where you can get the code and say the valve is moving slowly. The valve position is more for this load, and gives you all the temperatures high, etc. All the diagnostics messages are being given by this digital valve controller. Right. Now this covers the end of part 1. Now I shall start, it's about 11 o'clock. Professor, I got time only till 11:30, isn't it?
Yes, sir. Yes, sir. Yes, sir.
So I must try and finish the other 2 parts in that. So I'll go through the salient parts.
Okay, sir. Okay.
All right. I'll go down.
Yeah, sir. Visible. You can continue.
Okay, thank you. Now, this valve here in this, I'm going to explain to you the 2 important points and tell you that the valve has got a difficulty managing the process dynamics. This is an example of that. Process dynamics, I'm not going to dwell too much because Dr. Prakash had already talked about dead time, time constant, gain, etc. The loop gain also he covered, so I'll just show you the important part of the loop gain. Now, control valve coefficient, I'm going to spend some time. Sizing philosophy, I'm going to spend time, little bit, and control valve characteristics. Okay, and the inputs required that you can read also. Now, the fundamental point is the whole control valve manufactured by say 8 or 9 industries. So there has to be some common factor in that. The common factor is how do you sell the control valve? The control valve is sold. You want to know how much is the flow rate, because that's the control valve operates on the flow rate control, basically, whether it's controlling temperature or it's controlling pressure or controlling level. Some liquid has to go through this, and then the valve has to move up and down or rotate to give you the change in flow, which controls. So then what happened is, some many years back, the well-known company called Maheshan in US, they devised a simple method which became an international standard. They said, let us generate a new expression called control valve coefficient. That's called capital C and small v, control valve coefficient. It is explained in a very simple way. I don't have a diagram for that, but you can imagine it without much of problem. It is like it's like this. What you do is, you take a huge tank of water, okay, and you fill it up so that the height is maintained because of overflow. You're allowing water to flow in and the tank will overflow, but the height will remain same. What is the height? The height is 1 pounds per square inch. The height of water, okay, and that height will be maintained all the time. The height which will be corresponding to 1 pound per square inch. Now, 1 pound per square inch, and you have to make sure the water is at 60 degrees Fahrenheit, because you've got a laboratory, you can do all that. And then you got an accurate flow measuring device, very accurate. And then what you say is, you put your valve which you have manufactured there, and then you keep the valve open, measure the flow, and then you say that the amount of water in US gallons per minute that flows across the valve, which is seeing a pressure drop of 1 psi, can be called as a CV, control valve coefficient. KV is nothing else. It is done in the other unit, meter cube per hour and bar and all that. So you remember CV, 1 pound per square inch, water height, and then receiving end, whatever flow you have collected, gallons per minute, that becomes a CV. So you got the CV. Let us put a number called CV made by, let us say, Emerson. That is, let us say 50. And you have another company like Emerson, I talked. Let me go to another thing. Siemens is making a valve. Same size of valve, 2-inch valve, a 1-inch valve, 50 is the CV. His CV, Siemens, the body structure may be slightly same type of valve, 53. Okay. Then we go to another company who's making control valves like our Indian company, Instrumentation Limited at Palghat. Now, what do they make? They have made it as 54. Same thing. Say, their CV has gone through the exercise of 1 psi drop, and the amount of gallons per minute, as per the stipulated condition, that you got a 50, you got a 53, and you got a 50. Okay. Now, what do you do with that? So you got some common currency, you can say. In the control valve world, you got a common currency. Now, why do you require it? You require it for this. Because you are the process engineer or instrument engineer or whoever it is, you are going to select a valve for your plant. Now, selecting the valve, it all has to go through this formula Q is equal to CV, that's the control valve coefficient I'm buying from Emerson. Then, and your square root of delta P divided by SG. Let us for the time being assume that we are using only water, so that it will get rid of this SG. So basically square root of delta P. Now what is delta P? Is P1 minus P2. What was the delta P in the laboratory testing CV? It is 1 psi. So when the plant engineer requests you to procure, he will give you all the data, and his delta P may be 300 psig. We don't know. So he'll give you the size, everything, and so you'll arrive at this CV. You got Q. Sorry, you got Q with you because the plant manager has told you to do that. He has given you delta P, and he said the line size is so much, please select a valve. So what you do is you got Q, you got delta P, you do not have CV, and you got SG also, specific gravity output. So what you do is you calculate your CV, and then you float an inquiry or a specification. You send the specification to Bailey, Siemens, Instrumentation, Palghat. Now, all three will quote. They'll say for this particular process data, I'll give you a valve, CV 50, the other man is saying 52, the other man is saying 55. So then it's your game you have to play. Now comes the crunch. This is the most important statement in this part to kindly, just focus on what I'm telling you. It will answer all your questions when it comes to control valves. This delta P is a very comfortable figure of 1 psi in your lab, nice air-conditioned lab in a college or in a research institution. It's very nice to have delta P1, and you have to have this particular CV number. You evaluate it from there. So a lab delta V is delta P. Is different from the other delta P's which you come in the real world. Like I was telling you, on the lighter wing, driving on the Hebbal flyover in Bangalore is an absolute nightmare. So that nightmare comes when this valve is transferred to the plant. And in the plant, what happens is the process man says, my flow rate at say 335 psig, just a figure I've given. I have delta P for maximum flow is 35 psig. Is just signed and given you the data sheet. Now the plant is commissioned. Now Q is equal to delta P into a constant. Forget about square root of delta P. Now, if your delta P, he says, let us take a round figure, like let's say 81, because square root of 81 is 9. Now, if you're very happy because it's 81, and you have also selected a valve. Now, what is the delta P he's getting? So Q is equal to CV, which is a fixed number. You have selected from Emerson, so it's 51, multiplied by square root of this delta P. You are very happy if it's 81. It is not 81. It is come to 64. So what happened? Square root of 64 is, how much is that? 8, 8 is 68. What was 9 has become 8. And it is changing continuously. And the core control valve is trying to manage this scenario. So, this is very important for you to remember. Let me repeat. CV has been calculated on a very scientific basis, and the CVs are published in all the valves, number one. That same CV is substituted, and you put the dial in the delta P, and you get the flow rate, and you're very happy because delta P 81 was giving you the flow rate. Today, the chap is saying it's 64. So it's come down. Another day, it's saying 49. So square root of 49 is 7. So the flow is reducing. So what happens is, when you size a control valve, they selected CV. What did you get? 50, 51, 54. What an engineer does is, I won't go into a lot of details. The CV that is selected finally from Emerson or Fisher or Emerson or Siemens or Instrumentation Limited will be the next high. That's where your experience and thing comes. If you oversize the valve, then you have a problem also. Why? Because when you do what Dr. Prakash was telling, is when the controller output goes, the valve should be somewhere between 50 and 60%, 50 and 60% open. Sorry, 60 and 70% open, which is a beautiful control. If you try to be overcautious and size a valve which is oversized, you will find it is trying to control between 0 and 25%, which means that valve will be not doing a job. Similarly, undersize it, you will find the valve is all the time open. So that is the beauty about this basic sizing equation. And what I told you is something important. Delta P is at the mercy of the process. And in that kind of a unsystematic kind of a environment, the control valve has to function. And that is the big challenge when it comes to getting a stable control. This one I will explain to you in a very simple way. That is, you got the gain of everything has got a gain, right? I won't spend too much of time. Process, valve, transmitter, everything has got a gain. Process, controller, transmitter, process itself has got a gain. Valve has got a gain. That is a given input. So much of air goes and dies from what is the output. So like that, everything has got a gain. And then the gain is all reduced. The units are reduced. And they say if you multiply all the gains, that is your process gain, valve gain, transmitter gain, everything, and controller gain, everything. If you get a figure 1, if you keep the figure below, finally, if you get the figure below 1, then you have a reasonably sensitive controller which is not going to be unstable. But if it becomes more than 1, it's very, very sluggish. So what happens is, this entire process, you do some tuning and bring the process to a reasonable shape. We are not going to talk about tuning because tuning will take at least twice the time, like 90 plus 90, 180 minutes. Even then, we won't do it fully. So coming back to this one is, let us assume transmitter is constant, your controller is constant because you have not altered anything. So the two players in this match are, one is control valve and one is the process. Then you are telling me, so the other products are not changing now. And the valve, the control signal, the control trace in the DCS is going up and down today. What has changed? Valve has not worked. The poor valve is managing delta P, which is swinging like anything. And the loads are changing. And this suddenly one day, then you manage to tune it. Another day you find the gain of the process has changed. Let us assume that you've got a magic meter where you can see the gain. And the meter shows that the gain was X, it has become Y only. Why? Because your heat exchanger has got coated. And then the other pump which is working by the side is becoming useless because it's not delivering. So the gain of the process is a lump figure is changed. So then you're stuck. Then sometimes you go and say, I cannot touch the valve. Valve is trying to do the best. So I'll go to the controller and I'll do little tuning and get that magic figure of less than 1 through controller tuning, which has to be done very sensibly. Okay, so I told you two things. Delta P is only a pipe dream. Delta P is not constant, it's varying and it's creating hell for the process control. That will never change. So then we go on to another important subject of, now this is a beautiful graph I want you to see. I'll show it to you after a while. Let me see. Now here, what I decided is I listened to all the stories and then I'm going to have 3 types of plug. You've seen that plug which I showed you for that profile plug. I said this is one kind of a project, the plug which sits onto the seat. This goes up and down. This is another, the other contour, this is another contour. So what I've done is, if I move from 0 to 100% the valve travel, this one will give a linear kind of a, that is 5 means equivalent, linear, so much flow. This, etc., it's a linear one. Then what happens is this one follows an equal percentage. I got number of formula for this. Please, when the slides come to you, please go through. I've covered, including the formula I've covered, but I don't have the time to finish it because I'm already running late now. So I will expect you to read it. You'll get all your answers. So you've got a linear. Let us not worry about that. This I'm going to come to a little later. This you got a linear plug and this is an equal percentage plug. Then what happens is, this is all designed on the base of your delta P. Oh, delta P is constant. So I will show my characteristic. So it's very cleverly done. So I have done this profile, I have done this profile also. So what actually happens in the real world is something totally different, which you're going to see now and get surprised also. Now, this is your P1 minus P2, delta P. This is your inherent characteristic of a valve. Okay, this is linear. Okay, you're very happy because it's linear. And once you put it in that terrific traffic jam, which I was talking about, the process media and the network of pipes in the refinery, this blue curve becomes a drooping curve. Now, this one, very important thing, is called an inherent characteristic of this valve with this plug profile which you saw. And your magenta color is what actually happens when the car is going onto their Hebbal flyover. So that means this is your real characteristic, which is not matching with this. Similarly, the equal percentage valve characteristic, what will happen is, I hope I got that to show you. Yeah, this is a miserable slide which you have to see to believe. See, what you wanted an equal percentage valve to do is slowly becoming a linear. And then the linear valve is becoming quick opening. So everything changes. So when I tell you that the control valve, we have to have all the respect, and not only respect, we have to have the sympathy, because when you do only controller in your laboratory or when you do simulation, etc., you take it for granted that the control valve is basically behaving itself. Actually, today I have spent, it's really going to be 1 hour 30 minutes. I got another 10 minutes to explain to you in a nutshell that is a pipe dream sitting in the laboratory. The reality is this. And the reality is the delta P changing, summarizing the whole sheet, upsetting the gain, the linear characteristic is changing and becoming quick opening, equal percentage is changing and becoming linear. What does the controller want? Controller wants, its dream is to get the output. I'm giving input of 5 milliamps. The output should be equivalent of that. The valve position should be equivalent of that. How it is done? They use an equal percentage valve because in that profile, it's slowly becoming linear. So this is, I've given you an elaborate table of various the question that you're going to ask me, before you ask me, I'll answer. Where do we use this plug? Where do we use that plug? Why we use this, etc. in the characteristic? The answer is there in the last few slides, so I'm not going to answer it. And it's a fairly a wild answer because it says you have your delta P so much, you put your sensor here, then you use linear, then you use equal percentage. But my experience of nearly 55 years in this game, I can tell you that like a broad spectrum antibiotic which a doctor gives, we normally engineers, practicing engineers, stick to the equal percentage because by and large it takes care of this, and we do the reasonable amount of tuning. So summarizing, you have to know that you're actually in a dream world in the laboratory, and what you see in the process, the main culprit is the swinging delta P. I've given you all the characteristics. You can see there's one very important slide I'm going to show you. And after that, I will take you to, this is one of the, I would like you to see this slide. Please note down in your mind. It is, I think, in, I can't read it, 739 or whatever it is. I can't see. But this colorful slide will tell you the myth about delta P. It's a beautiful slide. I liked it very much. That's why I'm giving it to you. The delta P, we say, I got a flow of 100%, so my delta P is like this. I got a flow of 50%, I'll get so much throughput, I'll get. Pipe dream. The delta P reduces like anything and erratic. What are you getting? You're getting total haywire, everything goes haywire. Now to explain that, how the P1 minus P2 changes a beautiful slide. If you go through it, you will understand at least the myth about delta P. I think this is a very important slide for you. Now, this one I'm going to come, and not bad, I'll be able to finish it. This very just the axis. This is your valve somewhere here, P1, and this is your P2. Just this slide will come again in another 5 minutes. Okay. No, I'm going to, these things I'm not covering. Please read this. This is very hard to cover now because I just don't have the time to cover it. I would have loved to have another 1 more hour. It's not practical. So this is your, this one. Now, a curve which is nicely. Now I'll take you back to that old simple valve which I showed you in the initial stage. That what is that? It's shutting or opening. Now it doesn't have any profile, it's got only a disc. That valve, the moment the signal is given, the seat is lifted, the plug is lifted from the seat and water flows fully. That is called a fast opening valve. Okay, that is used for emergency shutdown, which you are going to see tomorrow afternoon. I'll explain that valve to you at that time with some more of inputs. So I have explained to you, this is the most important statement, inherent characteristic of a valve and installed characteristic of a valve. The whole personality changes with this installed and inherent. Okay. Now I'm through with this slide. I'm going to the last slide now. Yeah, this is a very odd slide. I could say I'd like to use the word odd, which I'm going to tell you very quickly. You have to read it. Now we have come to, we were quite comfortable in driving in the Hebal flyover. Now imagine that you're driving in a crowded place in a hill station where the roads are also uneven and narrow roads and trucks going by the side, and also the threat of wild animals and whatnot. So that is a difficult situation. So what is that equivalent difficult situation? This is called high duty control valves, and the problems, there are problems that are listed there: flashing, erosion, cavitation, choke flow, noise, material of construction, and anti-cavity strips, etc. Now I will lead you to that graph. I'm not going to explain vapor pressure. It's a physical chemistry. It's written there also. I think I have to go back to that slide. Professor, if I take another 5 minutes, it's okay?
Yes, sir. Yes, sir.
Because I may have a little problem in finishing. Yeah. See, there is, the whole controller of my talk now is the vapor pressure. The vapor pressure above the liquid changes. When you boil water, the pressure is how much? It's atmospheric pressure, 100. At atmospheric pressure, the water boils and opens. So the pressure is around 14.2 psi, whatever. Now, with temperature, the vapor pressure goes up. Now you see what happens. Your control valve is somewhere in the middle. Is my slide clear to you, the participants?
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Yes,
The
sir.
very important point you have to note now, the pressure is dropping like this. Why? Because there's a restriction of the control valve. Then what happens is, I have marked P2, PV. Now this PV is the enemy we are going to talk about. This is called the vapor pressure. And this is a shifting line. Okay, I'm deliberately shifting this line. So what happens, and it so happened to your bad luck, that this PV is stationed here. And when the PV is stationed here, the dropping, and what happens is it is getting below that. Then the trouble starts for you. It gets below, you had it. If it goes below, then what happened? Two things happen. Your delta P, you're putting P1 minus P2, that's not changed, because at that point of time, everything is going. But you suddenly find at the other end, the control room is telling array, I'm not getting any flow. This is what a joke it is, because you got a delta P, the valve is open, nothing is blocking it, and still you don't have a flow. That's what is called as choke flow. Now, why do you have a choke flow? The choke flow happens because of the condition of the hydraulics of the liquid. Then the liquid transforms itself at this kind of a vapor pressure and drop-in pressure into a completely an army of bubbles. Bubbles, very, very minute diameter bubbles, small balls, and they completely crowd, and not only the crowd, they completely erode the plug. You saw that plug with a profile, it's eating that plug. This is called flashing. This is sin number 1. Sin number 2, which is a deadly sin, is the pressure has dropped up to here for strange reason of hydraulics. After crossing that red unwanted line, it goes up. Then you had it. What happens is the little bubbles inside implode. And you know what's the pressure inside that bubble? 100,000 pounds per square inch inside the bubble. You cannot believe. That's the beauty of that theory of flashing and cavitation. The moment the pressure tries to recover, then you have what is known as a flashing action, and the destruction is more. It not only destroys your valve, it destroys your pipeline on the other side. So the point is, when initial part of the slide, I told you that this multidisciplinary, I was emphasizing multidisciplinary. This is what I'm saying. The multidisciplinary means immediately, if this happens every day, the company will have to close down. So how do you solve the problem? There are ways of solving this. So we will now see the damage. Now, this plug was looking respectably like a normal profile plug. This is how this is the shape it became after suffering that cavitation, bombardment. Okay, this is also a cavitation bombardment. I think there's one called flashing, which is also similar to that. This is the flashing to cavity. Now I'm going to take 1 more minute of professor's time to explain my own experience, which will take about 1 minute only. Then I'll close. I was commissioning a urea plant in the year 1981 December. I remember the date, along with my Japanese friend from Toyo Engineering. What we were doing, is we were trying to check the level control system from the control room, and the valve was seeing again process media, harsh process media. We used water. We played a small trick, and we said we cannot use the original material because the original material no one will give you to do a trial. So we used water, and we had that plug and stem, etc., made out of stainless steel, SS304. So stainless steel 304 was installed. And then what is the upstream pressure? Now you all know P1 in my case was 3,000 pounds per square inch. And what was the downstream side? It was something close to 2,000 pounds per square inch, downstream side. No, sorry. Let me repeat. Upstream was 3,000, downstream was 300 psig, 300 pounds per square inch. Then I remember that engineer Takada and myself, we both said, okay, we got the clearance at a 3.3 kV motor pump, and we started circulation. And the trial was to be, make sure that all the rubbish in the pipeline is removed by opening it and closing it, etc. And then they're ready to put the gold-plated control valve internals. You will be surprised that after 40 minutes only, we stopped the machine. We took the valve out for examination to see if there are any kind of damage of the inside, because any particles, welding rods can come in. What we saw was this: 40 minutes of running of a beautiful stainless steel plug. This is exactly how it looked. Now, perhaps cavitation, perhaps it is flashing. I cannot tell you the hydraulics of it, the reality. Then, the next question is, before I end, we did a trial after that using the right kind of plug. This was a sacrificial goat. This we wanted to sacrifice because we can't. Then we got a costly plug and seat, and then we installed it, and that was made out of titanium. Okay, then I was also the engineer looking after that plant. After 1 year shutdown, as per my list, I had to see the valve, the plug. The plug, when we removed and saw, it was as though it was new. Now, my dear friends, that is the beauty of metallurgy. That's the beauty of knowledge of other disciplines. You have to have a multidisciplinary approach when it comes to control valve. It is no longer only the electronics or the mechanical or the electrical aspect. It is and process. Last but you must know in and out of the process. The world of the control engineer in a process plant is you have to carry multiple disciplines in your head. Professor Prasanna, with your permission, I am bringing this to a close because I would love to continue, but it's not right.
Okay, sir. Okay, sir. Okay.
I hope you found it useful because I managed whatever knowledge I had.
Sir,
yeah,
recording your session, as every day we come across home, you're using taps as a control valve.
Yeah.
You are call the plumber for every time to service. Actually,
yes.
We don't know that. If you're going to use the borewell water, that is going to make a slurries and that in pipes.
Yes, yeah, absolutely. Absolutely.
That will not give the full pressure.
Yes.
That is not a beautiful pressure because you are unable to find out the problem every day. You want to call the plumber to clean that one.
Yeah. Because you don't have the strainer also.
Strainer also. But you exposed to that field.
Yes.
Our chairman, beloved chairman, to give vote of thanks.
Yeah.
Sir, Professor Harish sir. Hello. Harish sir.
Sir, there is one question in the chat box.
Yes, sir. Tell me.
What will happen to physical durability under repeated cavitation?
The physical durability on repeated cavitation. Now, a very, very lovely question. I didn't have the time to answer that. See, first of all, you have to establish that there is cavitation, and your question very well framed. What we do is, if we know cavitation, first of all, should not happen. Why? because when you design, choose the process conditions correctly, you make sure that the flow rate and the temperature that you reach, the vapor pressure, that red line I showed you, that pressure line should not cross that particular line. Your downstream pressure should not cross. So number one is your operating condition itself, you try to manage. That's the first method. Second method is, if you want to play safe and spend a little more money, the internals of these valves can be redesigned, and they are called anti-cavitation trims. That is, it will not be profiled like this. It will be profiled like, I think, hope I got it for you to show. Yes. This is, sir, your question is very nice question. So this is an anti-cavitation trim. That is, you don't have a profile plug. So if you know that cavitation is going to come, that you will have to work out in the design itself. If you know the operating conditions and you know you're going to likely to cross that red line of vapor pressure, which is prohibited, then you can use this cavitation trim, in which case what happens is the delta P that takes place, such a big drop in delta P does not take place, but it takes place in small quantities within this itself. Say P1 to P1A, P1A to P1B, P1B to P1C. Then slowly and slowly it becomes P2. So that means all the beating is taken place by dropping the pressure very, very scientifically. This is called an anti-cavitation trim. Very nice question, sir. So you will be able to, but the point is, if you have not been taking care of the operating condition and you are not aware of the red line, definitely you will have cavitation, and then you will face the music. So by anticipating and getting the cavitation condition in your design side itself, then you can, if you have any doubt, the question you ask is very sensible. If you have doubt, go for an anti-cavitation. Or the material of construction of the valve has to be, say, hard-faced so that it will not wear out, like sterlighting and other kind of coating. You got number of, unfortunately, sir, I could not complete. I have so much more to say, but I had to stick to the time.
Okay, sir. Okay, sir.
5 ರ್ಯಾಂಕಿಂಗ್ ಚೆನ್ನಾಗಿ ಬಂದಿತ್ತು, ಚೆನ್ನಾಗಿ ಒಂದೇ ಎರಡರಾಗ ಇಟ್ಟಿರ್ಲಿಲ್ಲ, ಈಗ ಮಾಡಕತ್ತೀನಿ. ಎಲ್ಲ ಶಬ್ದ ಮಾಡಿದ್ದೇನೆ, ಅವ್ರದ್ದು ಇದೆಲ್ಲ ನೋಡಿರ್ಲಿಲ್ಲ.
Can you mute everyone?
Sir.
All right. Thank you very much, Professor Mr. P.S. Krishna, sir, Principal Consultant, ICT, Industry Connect Technologies. Sir, we are extremely delighted to see your content-rich slides and your wonderful and fascinating presentation, where we have been witness to your vast experience and expertise in the area of controls, and how the control valve as a principal control element plays a very important role in process industries. And I wish we could hear more of you with respect to control valves itself, because I never imagined that there is so much to learn from control valves alone. And it has been a wonderful learning experience for all of us, and I am sure all the participants have enjoyed your presentation, and it has ignited interest in pursuing their learning in this area of control in process industries. Thank you very much, sir. On behalf of the Department of Electrical Engineering, UVCE, Bangalore University, I take this opportunity to place on record our sincere appreciation for your time and effort in participating in this faculty development program, and address our teachers,